All right. So yes, so I'm David Rapetti, a U.S. scientist at NASA Ames, and also affiliated with CU Boulder, and where this work is a continuing collaboration with Neil, Joshua, and Jack that will speak about related terms in the Astrophysics II session. And here I'm going to focus on the pipeline that we've been developing for over 5 years now, which it aims at pursuing the exploration of the dark ages and the cosmic dawn that Steve was talking about, and Yvette as well. So Steve made a nice description of the science goal that we have here, so I don't need to go into that detail, and in interest of time, focus on what we're trying to do here, which is separating that signal from the systematics. So we have important systematics that is mainly our galaxy and all the galaxies between us and the signal, as Steve was describing. And in addition to that, so in addition to this being much brighter than the signal, we have limited information on each of the components of the main systematic, mainly the foreground itself and the beam, the large beam that we have for these instruments, the knowledge of this beam. So in addition to that as well, we have also unknowns in the signal, as again, Steve also was describing, due to the fact that there's various astrophysics that we want to measure, and that it could take place here, and we don't, there's different models to describe it, as well as cosmological signals, as Joshua also will describe more in detail, for example, in relation with that map. So with all that, we look forward to the next, to a coming observation from the lunar far side, that is a pristine environment in radio from Roses and Lucy. Roses on the near side, so we hope at least to describe the foreground and the beam, and Lucy on 2025 on night observations to first attempt to separate the signal from the far side. So how we solve these problems is what I'm going to discuss here. So in order to deal with these uncertainties, what we do is generate sets of realizations from all the information that we have. Okay, so the information that we have can come from models, can come from observations, can come from simulations. And in order to put all this information on the same footing, what we do here is generate, again, realizations in the same way for each of the components on the data. Mainly here, I'm going to focus on the beam, foreground, and the signal, but we'll have also the receiver mentioned later. So in order to describe the main variations of all this information, we use a singular variable composition, and this is going to give us the main modes to describe each of these data sets. We're going to build a linear model with that, and then we're going to ask physical tools like, statistical tools like the information criteria based on evidence, how many of those modes are relevant for the description of the system. Okay, so with all that, we show with simulations, as we can see in the plots at the bottom right, we show with simulations that we can extract actually this signal. So the next step here, well, this is just a summary actually for your reference of the 4 papers where we describe the main framework of this pipeline, and also the publicly available codes that you can use for such experiments or other experiments as well, available on GitHub. PyLonX is the main part of the pipeline where we do separation components, the separation of the components and constraints, PERSYS for foreground description, and areas for signal modeling. So as I mentioned, and here in the central plot is the idea of the pattern recognition for building linear models of all the components. But one of the advantages of our pipeline is that actually all this technology we can use to focus on the differences between the signal and the foreground, and the beam weighted foreground, mainly the fact that the foreground changes in time while the signal does not. So our pipeline is particularly well designed for this purpose, so we can use different views of the sky, as many as the errors allow us. So normally it will be 10 different beams or so in time, and then we can use also different polarizations. So actually the foreground is polarized while the signal is not. So leveraging this information, we can make this separation more powerful. And then what we do is go from the middle here on paper 1, what I just described was in paper 3, and then we go to paper 2, where we actually put constraints on a nonlinear signal. In the middle, we had the linear signal, then we convert it into nonlinear, which is normally what we'll be interested physically, and we do a nonlinear analysis with an MCMC, which takes much longer, but we marginalize over all the foreground parameters, which makes it more efficient because this is an analytical marginalization, so it makes it much faster. So just one example of why these training sets or realization sets or uncertainty sets or modeling set, depending on what you want to emphasize, it's important. On the left, we have, like, for example, the horizon from the surface of the moon from a particular point. And if you only capture this horizon with one model, then you basically not going to be able to separate the foreground from the signal with this precision, as you can see on the bottom panels on the left. Okay, so in order to, so with one, even if you know the horizon, which again, the horizon blocks part of the foreground, so it's important. So if you know the horizon even well, but not well enough, so even with relatively precision, with one model of the horizon is not enough. So instead, we add a few realizations based on the uncertainty, for example, in the position of the instrument, in the measurements of the horizon, as you can see on the right, and then we can actually powerfully extract the signal with this technique that I've been described. So this is important in this technology in order to make these precision measurements. Then we can actually add, as well as I mentioned before, we can add also the receiver onto the system for the completion of the pipeline. This includes nonlinearity, which is the fact that the gain multiplies all the other components, the signal for the foreground and the offset. And we can deal with that as an extension of what I was mentioning before of the treatment of linear and nonlinear parameters. Everything that is nonlinear, we use an MCMC technique of similar kind, and then everything else we marginalize analytically. The gain is going to be always MCMC, that the signal can be both linear or nonlinear, and the foreground and the offset here, we treat them as linear, so therefore we marginalize over them. And this is important, as I'm showing here, because when you look at all the parameters, this is the full covariance of all the parameters, you can see there are many parameters, but especially they dominated by the foreground parameters, which is the box in the middle. Right? The box in the middle, they have many parameters because we want to describe the foreground in detail, as I mentioned, different polarizations, different times, okay, in order to have enough a powerful description of the foreground to separate it precisely from the signal. And all the foreground parameters are analytical, therefore we can marginalize them over, therefore we can do a very efficient MCMC with as many parameters as we want, in a sense, for the foreground. So this is the last main point I wanted to make, and then I'm just gonna put here my conclusions, which are the benefits from our technology, from our methodology, which, as I was been describing, essentially is the fact that we have these modeling sets in order to collect all the information that we have in order to make very efficient this very difficult measurement, collect information with theories, simulations, lab measurements, and so on. We can design these training sets for each experiment. We are ready to do this design for and build these training sets for Rosas and Lucy. For example, as I was mentioning before, we have full covariance information with our system. We can use all the correlated information from the time and the polarization to make a powerful separation. We can separate between linear and nonlinear parameters.
David, we're going to have to wrap up.
Yeah, and then finally, something that I didn't talk about that is a goodness of it. We also have include that in our analysis to validate the modeling sets. Thanks.